All right, good morning, everyone. So when I was first contacted by the board and invited to participate in this panel alongside Jan and George on this topic, I said, of course, my first reaction was how honored I was to do that. And then they gave me the title, and my next question was, what does that even mean? Because I think as John already talked about and came up a little bit in Jan's talk as well, when we talk about emerging models, data sets, and applications in climate and health, we often aren't talking about climate or health. We're talking about something mediating that response. And so if I'm going to talk about the emerging patterns, then I need to think about multiple fields. So I thought I'd take a couple minutes just to walk through the way I've interpreted this, heavily informed by the latest IPCC report, and then talk about some trends and opportunities. I'm not allowed to talk about challenges, and so it'll all be glowing, and then new directions. So what do we mean by this? So, of course, if climate conditions were like invading aliens that killed us in our sleep, things would be simple. We'd simply know what we needed to know for data sets and models and figure out how it's going to impact our health, right? But we know it's not like that. And so I'm going to break this down to three categories that roughly correspond to the way the IPCC has suggested we think about this. All right, and the first is that I'd say that any climate impact on health is mediated by other physical environmental factors. There's no such thing as a direct climate impact. You need to think about the hydrology, you need to think about the built environment, you need to think about structures. And that's true even for these so-called direct impacts like storm surge and heat waves. Things get more complicated when you start thinking about ecological mediation, and these are things the IPCC calls naturally mediated. And so the classic examples there are infectious disease, pathogens, and as well as allergens. And we can all think of more examples that fall in this category where it's both the physical environment and then some kind of biological or ecological process. And then finally, we have these, we might consider the most indirect or the institutionally mediated impacts. So a famine, right? Climate change doesn't cause famine. And so when you end up getting involved in these kind of socio-political factors that mediate the impacts, then you have yet another layer to consider. And one could argue that these don't have to happen in order, but I think that anything that's institutionally mediated almost always has a physical and an ecological component as well. And I do want to emphasize that I don't mean that the institutions are the humans, right? The human dynamics play in all of these things. Humans modify our physical environment. Humans are deeply involved in these ecological processes, as well as the institutions, of course. And so we can't just think of this as working from molecular physics up through political institutions. We need to think about the humans throughout. Okay, so and all of this, of course, feeds into some kind of health system response, which is what we care about in this context. Now, if we're going to talk about data sets and models and applications, that means these are the kinds of fields that are getting involved, all right? So it's not just climate science and doctors. We have to worry about this massive list, and I just stopped typing when I ran out of space in each box, because pretty much every community is involved in this along with their tools, okay? And so we need developments in all of these fields, and as well as developments happening, exciting things happening in each of these fields can help us in understanding the climate health link. Okay, so here are just a few examples of trends and opportunities. So those of you who know me know I'm a physical scientist, so this will be biased towards climate science and hydrology because that's what I do. But I'm going to try to overview a few of the opportunities we have across the spectrum. So first of all, thinking about the physical environment. So these are going to be like the direct impacts that aren't overly mediated by ecological and social processes. And I'm going to quickly point at 4 points that I think are interesting opportunities in data sets and models. And so starting off with new satellite capabilities. And so I need to just at least have a couple of things here. People in this room probably already know, but some of these NASA missions and ESA missions as well that have come up recently or upcoming are going to be a great opportunity for us. So the Global Precipitation Measurement Mission, GPM, the Core Observatory shown here launched last February. And so those of us, people like me who work mostly in the developing world, these data are invaluable, right? I mean, this is game-changing. GPM, you might be familiar with the predecessor TRIM that gave us the tropics at 25-kilometer resolution. GPM is part of a constellation of satellites that's going to give us sub-10-kilometer resolution, sub-daily for precipitation globally. And important for the developing world, I'd argue also important in the developed world because it is spatially complete and somewhat independent from other data sets. It's going to be great for inputs to environmentally mediated models. Second mission that I should mention is SMAP, the Soil Moisture Active Passive Mission, which will launch in January. Really this time? It's going to launch in January. And it's going to be giving us unprecedented information on soil moisture, okay? Better resolution, as well as it's got some active radar capabilities that are going to allow us to see through vegetation in some environments that we can't see through right now. Okay? And so if you're worried about puddles forming for your mosquitoes, well, SMAP won't tell you where the puddle is, but it's going to tell you what the soil moisture saturation conditions are in a way that we haven't known before all over the world. The third satellite capability I want to mention that is not a satellite at all, but it's this whole idea of accessible data portals. Okay, so NASA Giovanni, which I don't know if any of you use that, but it's an example, and I think one of the better examples, of how we can deal with these massive, obscure data sets and make them available to people who are working in the applications world. So it used to be that when I was approached by someone in working in epidemiology or public health and they asked me for some kind of precipitation analysis, soil moisture analysis, I'd say, okay, great, I'm a little busy, I'll get to that for you sometime in the next 6 months. Now I say, go to Giovanni, see what you can get there. It will data mine the entire NASA archive of certain sensors and models and give you some results. Now there are caveats here, right? Now all of a sudden we're making accessible data that are not perfect truth, that have the limitations. We want to be sure that people are working responsibly with the data. But Giovanni is really going to speed the process by which we can take this information and apply it to some of our health questions. And they're in the process of restructuring the entire thing to make it an open platform so that other institutions don't have to, and even independent researchers don't have to build it themselves. You can end up posting your data to Giovanni and allowing data access through there. And that's going to be happening in the next year or two. And again, a really great opportunity to democratize access to these data sets. All right, so you can't afford a satellite. And so you want to do something local and think about where the new trends are there. And I think that a lot of us already know this implicitly, that the availability of low-cost sensors is just transformative, all right, for a lot of what we do. And so here's an example that I'm showing. We're working with the Maryland Institute College of Art on this. And what we did is we had the art students develop a radiation shield, all right, that's adorable, that is also high albedo and does all the other properties you'd want for good meteorological monitoring, okay? And this is just an eye button that's doing temperature and humidity inside. So we can make these, you know, for $50 a piece materials, and I don't mean like $50 plus 3 months of lab tech time soldering things in the lab. It's like $50 plus a little bit of time to cut out and do the origami, right? And so it's really easy, and you can put them everywhere, right? And so this is East Baltimore. I don't know if you can see that in this light. But just, you know, we're talking block-to-block scale. We can put these everywhere. We are putting them everywhere in order to measure things like very fine resolution variability in the urban heat island. This is now just, I haven't even put a legend on this, but that's a Landsat satellite view of temperature. But of course, a satellite temperature is a radiometric temperature. That's not the same as an air temperature. It tells you nothing about humidity. So what we want to do is get this kind of health-relevant variable, the air temperature and humidity, and see if we can then develop some regression models with the satellites using this low-cost, high-density network. All right, and I should mention that these dots here, the green, I don't know if you can see, the green ones are schools, the other ones are households participating in a Johns Hopkins study on COPD or asthma. And so we can station these at places where we have health outcomes information and start really digging into what's happening locally with some of these climate processes. And as we know, during heat waves, the city can be 10 or 15 degrees warmer than the surrounding area, and so we expect a lot of our impacts to be happening here in a warming climate. Last thing on sensor webs I'll just mention is the one that we all know about, which is our cell phones, right? And so anyone who has an Android operating system and has not yet installed Weather Signal, please do so. And so Weather Signal, it's a European company, so they got better coverage in Europe, but it's free. And what it does is it tells you the temperature by monitoring the cell phone battery's cooling system, all right? And it's not a good measurement. It's a terrible measurement. It's wrong every single time. But it's been shown in a publication in GRL that if you have enough measurements, you get pretty good estimates at city scale, maybe even neighborhood scale of your temperature, all right? And so it's crowdsourcing data, right? And this is just one example, and I could go on about sensors for, you know, all day if we wanted to, about the new exciting things happening, both with cell phone technology, but other ways to get citizens involved in this research, which is a real opportunity for us. Okay, so you've got data, you've got your sensor web or you've got your satellite, but the problem is you want to do something like monitor Vibrio, like Jan was just talking about, or Vibrio risk. And so you look at the Chesapeake Bay, and on a given day, this is your coverage of something like sea surface temperature from satellite, because it's cloudy, it's hazy, it's hard to see the water, okay? This is a good day, getting this kind of coverage. And so then what do? Well, you do what atmospheric scientists have been doing for a long time and what the physical oceanography and land surface modeling community are doing more and more, which is data assimilation. So this isn't showing so well, but this is a very high-resolution grid of a dynamical model, the Chesapeake Regional Ocean Modeling System. And this gives us dynamical predictions of all the properties of the water. We can then merge this using data assimilation statistical techniques with the satellite to get results that are both high resolution and credible because they're informed by observation, and so you can get these spatially complete estimates of the variables you care about. All right? So these data assimilation systems have all kinds of applications. You can then take this and, for example, put it into a Vibrio, a statistical regression model to predict Vibrio vulnificus, for example. As Jan explained, we think we understand some of the ways this system responds to temperature, salinity, other variables, and then you can do this in near real time. NOAA already does something like this, but not with any satellite data. So right now we're working with them to get the satellite data informed so that it's not just a free-running model that we can't believe, but something that has a little more observational grounding. I'm not allowed to talk about, or I don't think I'm allowed to talk about challenges, but this paper where we actually talk about this will show that I think we're doing pretty well in the input data to the Vibrio vulnificus model. I think there's a lot of uncertainty as to what happens at the high end of that temperature range, like what Jan was talking about. Like as you move out a sample and you've got this complex ecological system, can we project forward for the Chesapeake anyway, or are we starting to see some maybe ecological response that is turning this off at the extremely high temperatures? But that's another problem. Another way we're using data assimilation in my group, so this is Peru looking at malaria risk, and we can put in a land data assimilation system, again, using a lot of satellite data and models to get things like surface soil moisture, soil surface temperature, and putting that into our prediction models to predict malaria with data from 350 health clinics around the area to understand what's going on there. Finally, on the physical side of things, the satellite era, we usually say it started in 1979, right? That's kind of the rule of thumb, that's a modern satellite era. So that means that this is his 35th birthday. And that's really important, right, because that makes it like a climate record. Once you get about to 30, 35 years, you start talking about capturing decadal scale variability in a way that you can say things about climate change. And so that's why, in our world, there have been a lot of neat papers coming out about this because it's happening now. And for the health world, that means that, yeah, we've got climate records going back 100 or 200 years if all you care about is trying to estimate global temperature. If you're trying to get a local environmental characteristic, you need to be in the modern satellite era. And so when we look at things like heat waves, now this is using a land data assimilation system, an LDAS, that incorporates satellite data. We notice that over the last 35 years, if you look at the frequency of days characterized as heat waves, if you use a temperature threshold, you see these maximum in the southwestern plains. If you use a heat index threshold that accounts for humidity, like the National Weather Service does, you see more in the southeast, okay? Interestingly, if you then look at the trends of this over 35 years, masked for statistical significance, you can see that temperature max heat waves are increasing a lot here in the Mississippi Valley in the southwest, but heat index maxima are increasing maybe Midwest and East Coast and not so much in the West. So in other words, the changes in the vulnerability spectrum are different depending on what definition you use, and we can use the satellite-informed data records to understand that. Okay. Ecological processes. Really quickly, a couple examples of how we're doing this. And I think there are opportunities in making our models more process-based and using novel data sources and thinking about coupling more. So as a climate scientist, my least favorite vector-borne disease is dengue, right? Because I have no chance at dengue as far as I'm concerned, because I can't resolve the places that dengue mosquitoes breed. Okay, malaria, cholera, it's like I got a chance. We're talking about like big, large-scale environmental sensitivities. But for dengue, it's tough, and so we rely on these questionable regression models to get at this. But what Andy Moynihan, Dan Steinhoff, and some other folks at NCAR are doing that's really cool is this WATCHM model, which is a great acronym. But what they're doing is they're doing a full energy balance model of the containers that dengue breed in, and they parameterize this with actual data, right? And so that they can then say, okay, what's happening to the water temperature here, using inputs from the kinds of physical data sets that I just described, and then maybe link that to something like this. This is called Skeeter Buster. It's a single enzyme kinetic reaction based model of the growth of Aedes aegypti, right? And so what you can then do is say, okay, I'm going from climate data not to a regression model, but to an energy balance model and into some kind of biologically properly formulated response. And so we're actually going to try to get the process here rather than just regress, which I think is important as we move out of sample. New data sets. So Orange Communications, some of you might have participated in this, did this really cool thing, Data for Development, where they released cell phone data for some intensive observation period for Cote d'Ivoire. Okay, so you knew where people were calling from when over this whole period. And you could do that. That data allowed us to put it into a human mobility model. You overlay the population data, and Andrew Asman, Justin Lessler, and some others of us at Hopkins did this, figured out what the human mobility model was, combined that with a data assimilation system that my group produced to get estimates of flooding, potential cholera reservoir size, and filtration of the vectors. And then you can put this into a dynamical epidemics model that says, okay, a stochastically seeded cholera event, how does it spread? Okay, so again, getting at process here, dealing with the ecology, as well as the human side of that ecology in the form of human mobility. Last example on ecology, we can talk about these coupled analysis systems, all right? So Amazon frontier malaria, all right? So people might be familiar with the frontier malaria hypothesis, all right? And so if you look at these images, these are just, you could do this anywhere in the Amazon, right? So this is some place in Ecuador, deforestation between 1986 and 2002, all right, satellite derived. So we have the satellite land cover information. But what we're trying to explain here is this observed process through which, if you look at the years since settlement on the Amazon frontier, and you look at the parasite index for malaria, it spikes and then declines. So you have an epidemic period, a transition period, followed by this endemic condition is what we face now. Now, it's endemic. WHO actually thinks this is one of the places in the world where we could eradicate. All right, they want to eradicate. They had the rollback malaria program going there for years, and so an interest for us in the research community is how do we do that? But the first thing is how do we explain this curve? All right, and the example I gave from Cote d'Ivoire a moment ago, that was an epidemic. That's complicated enough, but we're talking about epidemic time periods. We don't have to worry about things like changing infrastructure and cultural patterns. All right, it's fast enough that we can assume those are static. If you want to explain a coupled ecological system like this over a period of 15 to 20 years, it gets complicated because you're saying, okay, I want to link climate to my health outcome, and I know how I want to do that, at least, from the perspective of vector habitats, maybe land use change, how that feeds back on climate. So this is complicated enough, just trying to get this kind of physical ecological system as it interacts with human activities and land use. But now we have to worry about is how is the infrastructure developing, how are policies coming into play, what are the migration patterns in and out. We need to be doing population dynamics of the humans, not just of the parasites, all right? And so this, I'm still calling this ecologically mediated because I think this is all ecological, right? It's just a very deeply coupled ecological system that we need to understand. And so we're working on this. I don't have a results slide for you, but I think there's a lot of opportunity in this kind of integrated modeling. Okay, finally, on institutions, all right? So this, again, could be subject of a workshop or multiple books. But I'm just going to give one example. So here I'm going to limit myself to talking about how our social response from individual to institutional level might influence adaptation patterns and therefore evolving risk. And the example we're working on right now is an NSF project on what happens when you have multiple hits or near misses. Okay, so this is led by Seth Geikema at Hopkins. And this is post-Sandy, right? And the question is, okay, Sandy hits New York, then it gets hit again in the next 5 years, let's say, right? At what point do you start seeing serious behavioral change on going from like the cadastral level, I mean looking at like individual households, how they harden themselves to climate change or leave, up to the institutional level, like how many more times do we rebuild Far Rockaway, right? And so this is, you really need to understand this if you're going to understand what the true risk over the long term is of things like disasters. So we're going to focus we're focusing this study just on hurricane, storm surge, and heat waves, because we figured what are the two things we kind of know are going to happen, right? No one can question that this is going to happen. And so it starts off with, this is where people like me sit. Okay, let's do the climate scenarios to figure out how frequently we're getting these extremes, all right? But we immediately have to interact that with simulating the impacts on human health, certainly, but also on engineering, right? I mean, what are we doing to harden our infrastructure, and how has that changed the magnitude of the storm surge, okay? So you already have a coupled system there between the impacts and the hazard that involves institutional decisions. But what we really want to get are these behavior and choice agent-based models, right? To understand, again, from the individual scale to the institutional scale, it's like interview-type research, right? And very highly detailed economic research on individuals, business, and government to figure out how that is interacting with how we respond to the impacts, and then how that might feed back on the frequency if we start talking about adaptive decisions, for example, on the intensity of heat waves. Do we change our urban infrastructure in a way that makes the heat waves less severe, all right? And so this kind of research, so in working with the agent-based modelers on this project, I talk to them and I say, this is crazy. We can't do that. And we can't, right? But we can start understanding the pieces of the process, right? And building models that are useful thought pieces when working with decision makers on this. And we're never going to get it right, but we might make it, as they say, interesting in a useful way, okay? All right, so let's close up here with a couple things on new directions, okay, as I see it right now. And so two big themes that I'm going to mention here. One, in the climate science world, there's now a lot of talk about climate services, all right? And so the idea is, how do we go from this model in which climate science feeds on through with cascading uncertainties, with cascading actors, down to somehow tell the health system people what they're supposed to be doing, to a climate services model, which really, as we know, has to kind of be driven by this. You have to turn the arrows around, start from your decision process, and say, okay, how do I construct my data delivery system? How do I build my models in a way that's going to inform the decision with an adequate level of, I don't want to say certainty, but with an adequate level of risk characterization, right, that is going to allow for a useful decision to be made. And that was really easy to do in PowerPoint. It took me no time at all. This is like, I think, one of the grand challenges for us right now. We have this global framework for climate services, which is fantastic. We've got NOAA and EPA. We've got lots of people working on this problem. But how do you actually transform communities to think in this way and really rebuild our tools to make it work? Okay. Second thing I'm going to mention, I stole this slide. I think this was Bob Valario's slide from last week. I didn't credit you because I didn't know who at Department of Energy made it. This is a DOE slide. All right. And they had a workshop, really neat workshop last week. Several people here were involved in on coupling modeling systems. So to a modeler, this is what the world looks like, right? We have our integrated assessment models that tell us the future of society based on economics and social processes. We've got, and that's how the IPCC gets its scenarios and things like that. Then we've got our Earth system models, climate models, regional climate models, weather models, ocean models, et cetera, that try to get the physics of the system under a change in social systems. And then you've got your IAV, your impacts, adaptations, and vulnerability, which is where, in this diagram, I think not inappropriately, health sits over here, right? We want to know what the impacts are going to be on health. And one thing that was discussed at this workshop last week a lot was saying, okay, when and how does it make sense to make these models dynamically coupled, all right? Right now, we have this information flow that says, okay, here's our scenario, here's how the climate responds, and people die in Pittsburgh or something, right? And so can we turn it around in such a way and that, or is it worth the effort of making it a coupled way that involves health? And health is, at the far end of the impacts here, right? So what kinds of feedbacks might be important to capture? Well, for example, did the 2003 European heat wave have any impact on European climate policy? I think a lot of people argue that it did, or at least had an impact on how people think about these things. Fair? Fair, yeah. Did Sandy impact the way that people think about climate change, right? If and when people decide to actually do something about climate change, why will it be? Well, maybe it's going to be because of health impacts, all right? And so do we need to think at least loosely about how these health impacts might feed back on our system, all right? Maybe the answer is no. Maybe the answer is we've got bigger problems. But I think these deeply coupled processes are a really interesting problem and somewhere where the health community, as far as I'm aware, plays not at all right now, but might be an informative input to things like the integrated assessment models on how our policies are going to evolve. Okay, so just to close up, telling you what you already know here, this is a hugely interdisciplinary problem, but I do think that there are these exciting opportunities, new observations and access to those observations, right? The satellite data as well as the open data policies most institutions have adopted, and tools like Giovanni to get at those data. Data and model integration, so I talked about the data assimilation examples, but there are all kinds of ways to do this, to really start pulling information systems together to get higher quality information into our decision-making process. Process-based analyses like that dengue mosquito example. Can we move from a model of saying, I predicted your precipitation and temperature and gave you a prediction, to something more sophisticated, like what Jan presented on getting multivariate models that start involving migration patterns, and perhaps even to dynamically integrated models to understand those processes better. And then these interactions with behavior and policy. How does adaptation and institutional decision-making end up influencing our health profile so we don't end up doing things like projecting, unbelievable impacts, right? Because obviously people are going to change, all right? And finally, this idea that maybe we need some kind of new paradigm in the research community to think about climate services. We already say we're going to do it. What does that mean in terms of changing the way we all interact as communities? And also, is there any value in trying to capture these, what I'm calling deeply coupled processes as health feeds back on the entire system? So, thank you.
Thank you, Ben. That was an incredibly rich talk, touched on so much that I think we're going to be touching on over the next, unfortunately, only about 30 hours. We have time for questions for Ben. So.
web. If you have questions, please use the microphone, or speakers, please repeat the question.
Thank you, yes. So we have the microphones up, and also we are a small group, and I'm going to ask that if you do ask a question, the price of admission is telling us who you are. So,
Hi. George Daston, Procter & Gamble. You mentioned the difficulty in modeling agent-based behavior models and things like that. It seems to me that the economics world has been trying to do those sorts of things for a long time. What's the state of the art in terms of collaboration between economists and physical scientists in trying to do these models?
Yeah, so I think that in the world of the large scale, let's say, in energy systems, I think that some of our colleagues at DOE would say we're doing okay, right? The economists are core members of those development teams, okay? Most of my interactions with economists happens in the world of agriculture. I'm working on trade and impacts to smallholders up through large scale. And I would say that there as well, because we're pretty good, we've been thinking about commodities and food futures for a long time, there's a good basis there. If we're going to talk about in the health context, right, how the economics works into decisions on adaptation or on quantifying impacts of health, honestly, I don't know where that stands. There are probably other people in the audience who would have a better sense, but sorry. I
mean, thanks. That's a great answer. I guess one of the things I was thinking about, though, is, there are, every year somebody at the University of Chicago gets a Nobel Prize for predicting people's behavior in economic terms. And that seems to be more relevant to this idea that you have about, how long are people going to accept, or what price they're willing to pay to keep living in their neighborhood even though it's vulnerable.
Okay, sorry. Yeah, and that is an interesting question. And again, there might be other people more qualified. I would say that my experience comes through that hurricane heat wave project that I've been involved in, because we're working with Resources for the Future and other economists on that. And I would say that it is an exciting time in that research, but I don't think we have a good understanding of where that's going. But we understand that we have to think about it. But I'd certainly welcome any other comments from people who know more.
Hi, my name is Jerry Pogium with SOEH. I'm very interested in how one can use satellite data sets to actually precipitate better planning processes, move people further ahead on an action level, and I understand the complexity and the challenges. Earlier this year, we had JPL scientists and University of California scientists making use of the GRACE satellite data to look not only at the reduced flow in the Colorado River, but they actually looked at the reduction in groundwater that sends a signal about future water demands that cannot be met by that system, and that almost demand better efficiencies and alternative approaches. So do you have any advice about which systems now could help precipitate better practical planning in local health departments or states?
Yeah, excellent question. So I think the last part of what you said there is the critical question, which is whose decisions are we talking about? Local, state, various levels. So I mean, Jay Famiglietti's work on GRACE that you mentioned is, I think, a fantastic example of thinking nationally long term. Right. Myself, I do a lot of work with satellite data in the Nile Basin, where it's a nice, transparent and credible approach that all stakeholders can agree to try to figure out the water balance. Right. So that objective source of information is good. If you're talking about as you get more and more local, it gets harder and harder for people who work with satellite data. And so in that sense, there's a technical answer to your question, which is data assimilation systems, downscaling. There's a lot of research going on that to produce products, but your uncertainties cascade. And so I think the better answer, not vague and therefore better, is again this idea of turning the arrows around and saying, okay, which specific decision maker are we talking about? What's their decision process, and then how can we work up from there? Because I could rattle off amazing satellite capabilities for you right now, right? But they might not be relevant to that decision, and they might not have the precision or the accuracy that is needed for that result. And so can we turn it around and take your question apart and make it a million separate questions about what each decision maker needs? And if we can do that, I think that there's a role for various satellite observations. Yeah, great. All right, thanks.
Thank you very much. Those are two excellent questions, and I think the first question, hopefully we will come back to, about integrating economic thinking into these kinds of questions and these risk models. I think there's a rich question there, and of course the second question is a great segue to our next speaker. But before we go to our next speaker, I just want to touch, Ben, that was really a great talk, and I'm just going to pick out 4 things that I think you brought up that really will resonate through the course of the workshop. The first is you touched on the fact that often with our data sets and with the modeling we're able to do, we are modeling not the health outcomes, but we're modeling the exposures and the risks. We're able, with some confidence, to figure out where the bacteria might be, or, you know, thinking about the mosquitoes, without being able to actually say how many cases of dengue or how many cases of Vibrio. But that's still very important, and that, you know, part of the issue is how do we go from that to a better estimate of the health outcome. But just the idea that we focus on the risk and the exposure, because that's what we can do now, is one important theme. The second is this idea about moving from regression models, you know, just observational models based on just statistical correlations of behavior, to mechanistic models, like you did with the Watchum, is the second thing, and the agent-based dynamic model, you know, kind of more mechanistic rather than just looking at current observations and regressing and then trying to, you know, put in new parameters for climate change and see what the answer is. The idea about advancing piecewise, doing what we can do, what you talked about with the agent-based models and in large integrated systems, the way we're going to make progress is just working piecewise until we can get the more integrated picture. And then the last thing about integrating health into these large impact assessment vulnerability activities, bringing the health community there. That's one of the reasons we're having this workshop. We will definitely be coming back to that. But next, to answer this question about whose decisions and what is the public health world requiring in terms of models and information, we have the best person I can think of to speak of this, Dr. George Luber, who is the director of the Climate and Health Program at the CDC, colleague of mine on the Interagency Work Group on Climate Change and Health, will be here to speak with us about his projects and how the public health departments are trying to answer these questions. Dr. Luber?